Hey everyone, and welcome. Today we're diving into the amazing physics behind medical ultrasound. We're going to explore how we can use sound waves, ones we can't even hear, to create these incredibly detailed real-time images from inside the human body. It's fascinating stuff.
So, here's the game plan. We'll start with why ultrasound is so important in the first place. Then we'll get into the magic crystal that makes it all happen. We'll follow the sound wave on its trip through the body, see how the machine turns faint echoes into a clear picture, and then we'll actually run the numbers to see the physics in action. And finally, we'll wrap up with a quick quiz to see what you've learned. Let's get into it.
Okay, first up, why do we even need something like ultrasound? Well, it all boils down to a huge challenge that doctors have always faced. I mean, think about it. This is the core problem, right? For most of history, if you wanted to see what was wrong inside someone, you had to cut them open. Then, we got things like X-rays, which were revolutionary, but they come with their own risks. So, the question remains, how do you get a safe, clear, and live look inside? And this is exactly where ultrasound comes in and just shines. X-rays use ionizing radiation, which, can damage cells over time. Ultrasound? It just uses sound waves, really high-frequency sound waves, but sound nonetheless. And here's the real kicker. It's not just safer, it gives us moving images in real time. We can literally watch a heart valve open and close. You just can't do that with a static X-ray.
So how in the world do we generate these special sound waves? Well, the answer is pretty incredible. It involves a really cool bit of physics and a very special kind of crystal. First off, let's just be super clear about what we're talking about. Ultrasound literally means beyond sound. It's any sound that's at a frequency way too high for humans to hear. And for medical imaging, we're not just talking a little higher. We're talking in the megahertz range. That's millions of waves per second.
Okay, so the absolute heart of an ultrasound machine is something called a piezoelectric crystal. Quartz is a great example. If you could zoom all the way down to the molecular level, you'd see its atoms are arranged in this really neat way that gives it a natural electrical charge, kind of like a tiny magnet with a positive and a negative end. This unique structure is the secret to everything.
Now this is where it gets really clever. If you apply a voltage across this crystal, its molecules try to line up with the electric field, and that forces the whole crystal to physically change shape. It either gets squeezed or stretched. So what happens if you apply an alternating voltage, flipping it back and forth super fast? The crystal starts to vibrate, compressing and expanding millions of times a second. And that vibration? Well, that's what creates the high-frequency ultrasound wave. It's an energy converter. And here's the most elegant part of the whole design. It's a two-way street. The effect is completely reversible. When a sound wave comes back, an echo, and hits the crystal, it makes it vibrate. And that physical stress on the crystal actually creates a tiny electrical voltage. So the very same crystal can be both the speaker and the microphone. Brilliant.
You take that crystal, put it in a case with some electrodes and a backing material to keep things clean, and what you get is this device called a transducer. This is the probe that the technician holds. Its job is simple. Send out a quick pulse of sound, then immediately switch to listening mode to catch any echoes that come back.
All right, so the transducer fires off a pulse of sound, but what happens to that wave as it starts its journey deep into the body? To understand this, we need to get familiar with a key concept called acoustic impedance. We just call it Z. You can think of it as a measure of how much material resists sound passing through it. You calculate it by multiplying the material's density by the speed of sound in that material. And here's the thing. Every single tissue in your body, fat, muscle, bone, blood, they all have a slightly different acoustic impedance.
So why does that matter? Because every time that ultrasound wave hits a boundary between two different tissues, say from muscle to bone, the difference in their acoustic impedance determines how much of that wave bounces back as an echo. The rule is simple. The bigger the difference in Z, the stronger the echo. This is literally how the machine sees the edges of our organs. But the wave doesn't just reflect. As it travels, it also loses energy. It gets weaker. We call this attenuation. It's kind of like hearing a sound fade into the distance. The wave's energy gets absorbed by the tissues it passes through, and that energy transfer causes a tiny, completely harmless amount of heating.
And this loss of strength isn't a straight line. It follows what's called an exponential decay curve, just like you see here. The formula basically says that the deeper the wave goes, that's the X, the weaker it gets. That little mu symbol is the absorption coefficient, and it's different for every tissue, which adds another layer to how the final image is formed.
So we've got these echoes coming back to the transducer. They have different strengths, and they arrive at different times. How on earth does the machine take that jumble of data and build a picture we can actually understand? Well, first, you have to solve a really big practical problem. As we're about to see in the math, the acoustic impedance of air is completely different from skin. If you just put the transducer on dry skin, almost all the sound would just bounce off. So you use a coupling gel. This gel gets rid of the air gap and has an impedance that's super close to skin, making sure more than 99% of that sound wave actually makes it into the body.
Okay, so the machine gets a signal back. The simplest way it processes this is called an A-scan. It's basically just a 1D graph that plots the strength of an echo against how deep it came from. But that's not very useful on its own. So what the machine does is sweep the transducer, collecting hundreds of these A-scan lines, and then it stacks them all together to build up a 2D image. That's called a B-scan, and that's the classic grayscale ultrasound image you're used to seeing.
And if you can build one 2D image, why not build a bunch of them really fast? If you string together B-scans in quick succession, you get an M-scan for motion. And this is how doctors can watch things happen in real time, like a heart valve flapping open and shut. It's just an incredible diagnostic tool.
Okay, we've gone through all the principles. Now let's get our hands dirty, put the physics into action, and actually run the numbers to see how this stuff plays out in the real world. This first example is perfect. It gets right to the point we just made about that coupling gel. We're going to calculate exactly how much sound reflects at the boundary between air and skin. So we use our reflection formula. Now just look at these numbers. The impedance for air is 430. For soft tissue, it's 1.6 million. The difference is enormous. So when you plug those into the formula, the number on top and the number on the bottom are almost identical. The final result comes out to about 0.999.
And what does that mean? It means 99.9% of the sound wave's intensity would bounce right off the skin. Almost nothing would get in. The scan would be useless. This one number perfectly shows why that simple bottle of gel is absolutely essential to the entire procedure.
Okay, let's try another one. This time, let's look at a boundary inside the body, where muscle meets bone.
The impedance numbers here are closer, but still pretty far apart. 1.7 million for muscle, 6.5 million for bone. We plug them into the exact same formula. The math works out to about 0.343. This means that at that boundary, about 34% of the sound bounces back. That's a strong echo, which is exactly why bones show up as such bright, clear lines on an ultrasound. All right, time for the final boss. This is a more realistic problem because it combines both of the effects we've talked about, attenuation and reflection. A pulse goes through muscle, hits bone, and the echo travels all the way back. How much of the original signal actually makes it? We got to tackle this in parts. First, we need to calculate how much the signal fades just from traveling 7 centimeters through muscle. Then, we need to figure out how much of that weakened signal actually reflects off the bone. And finally, we just multiply those two results together to get our answer. So let's look at the numbers. Step 1, attenuation. We use our decay formula. It turns out that after the 7-centimeter round trip, only about 20% of the original signal's intensity is even left. Step 2, reflection. We know from our last problem that 34.3% of what reaches the bone gets reflected. So, for our final step, we multiply them. 34.3% of that remaining 20%, which gives us a final fraction of 0.0686. That means less than 7% of the energy from the original pulse actually makes it back to be detected. This really drives home the point that the machine is listening for incredibly faint whispers. And that's exactly why the electronics inside have to be so good at amplifying these tiny signals.
All right, you've seen the theory and you've seen the math. Let's do a quick lightning round of questions just to make sure all these ideas are locked in. First question. So the speed of sound in blood and muscle is pretty similar, so why are their acoustic impedances different?
And the answer goes right back to the formula. Remember, impedance isn't just about the speed of sound. It's the speed of sound times the density. So even if their speeds are close, their densities are different enough to give them distinct impedance values, and that's what allows us to see the boundary between them. Next up, an ultrasound machine doesn't just amplify every echo the same amount. Why do the echoes that arrive later need more of a boost? This is all about attenuation. An echo that takes longer to get back is an echo that traveled deeper into the body. That longer journey means it lost more energy along the way, so the machine has to crank up the amplification for those later echoes just to make sure the final image looks uniform and isn't dark in the deeper parts. And for our last question, let's bring it all the way back to the beginning. What are the big wins for ultrasound when you compare it to other imaging methods like X-rays? Really, it comes down to 4 key things. First, it's safer. No harmful radiation.
Second, you get to see things in real time, which is a massive advantage. Third, the equipment is generally cheaper and way more portable. And finally, it's just so versatile. Doctors use it for everything from checking on babies to looking at hearts and kidneys.
So from a tiny vibrating crystal, we get a moving image of a living heart. It's just an incredible application of physics. It really makes you stop and think, what other invisible forces are all around us, just waiting for us to invent the right kind of transducer to see a world we never knew was there?